Hi folks, we're going to take a look at number 15 from page 111 from the Unit 1 assignment. So here they give us this function, and the first thing they want us to do is to determine the slope of the tangent when the function crosses the x-axis. Okay, so what we'll have to do is first determine what the x-intercepts are and then see where we go from there. Okay, so this is a very different function from the types we've been working with, but think about how you would solve, say, something like x cubed minus x, and if you wanted to determine the zeros here, well, you would do that by factoring to try to write this as a product of two other expressions. And here, what you factor out is the smaller exponent of x. So I'd be factoring at x, left with x squared minus 1. And you can then solve that. Okay, you don't want to factor out the larger exponent because then you'd end up with a negative exponent along the way. So I'm going to use that same idea here. Okay, I'm going to factor out the smaller exponent of x. So x to the 2/3. Okay, and let's see what we're left with. So 2, and here we divide out x to the 5/3 by x to the 2/3, and we're left with x to the 3/3, which is just 1. So 2x minus, and we factored out the x to the 2/3, so minus 5. Okay, so from here we see that the function has x-intercepts at 0 and at x equals 5/2. Okay, now here it says where it crosses the x-axis. So what we don't know here is, does it just touch the x-axis? Does it actually cross it? So, we'll find the derivative to see if that helps at all. Okay, now they do in B give us the graph for this function, but let's see if we can figure it out without consulting the graph. So let's find the derivative here. Okay, so here take the 2 times the derivative of x to the 5/3, so that's 5/3 times x to the, 5/3 minus 1, that's 5/3 minus 3/3, so 2/3. Okay, and then here minus 5 times derivative of x to the 2/3, so that's 2/3 times x, 2/3 minus 1 is negative 1/3. Okay, so let's clean this up here. So we've got 10/3 x to the 2/3 minus another 10/3 x to the negative 1/3. Okay, now the first thing I notice is that because of this x to the negative 1/3, that would go into the denominator. So that means the derivative is not defined at x equals 0. Okay, so it doesn't make sense to even be finding a slope of the tangent at x equals 0. Now, if you look at the graph that we'll look at in a second, given in B, we'll see that it does not even cross the x-axis there. But it doesn't even make sense to talk about a derivative of x equals 0. So we're really only interested at x equals 5/2. Okay, now this is where normally if this was a polynomial, I would say it wouldn't be worth simplifying the expression, but to put 5/2 into each of these expressions would be very, very annoying. So I'm going to see if I can simplify this a little to make my life a little easier. Okay, so here, well, they both have a factor of 10/3, so we'll take that out. And now I'm going to do the same thing that I did before. I'm going to factor out the smaller exponent of x. In this case here, x to the negative 1/3. Okay, so what are we left with? So here we divide out x to the 2/3 by x to the negative 1/3. So I subtract the exponents. 2/3 minus negative 1/3 is again just 1. Okay, 2/3 plus 1/3. So here I'm just left with x. And then on this side here, I remove the 10/3 and I've factored out x to the negative 1/3. And look how nicely this factors out. Okay, a lot easier to evaluate this derivative at 5/2 than in the original form. Okay, so let's put that in here. We've got 10/3, got 5/2 to the negative 1/3, and then 5/2 minus 1. Okay, so here 5/2 minus 2/2, so that's just 3/2. So 10/3, I'm just going to rearrange here, times 3/2. So that's actually going to be pretty nice. Now here, I'm going to see what I can do with 5/2 to the negative 1/3, but I see this negative here. So just to make my life a little easier, I'll, of course, apply that negative exponent. So that will give me the reciprocal of 5/2, so 2/5 to the 1/3. Okay, this here, the 3's reduce, 10 over 2 reduces to 5. Whoops, sorry, this should be 2 over 5. Just notice that. Okay, so now I'm left with 5 times, well, here I've got 2 to the 1/3 over 5 to the 1/3. Why do I do that? Because I notice that I've got same base, and I can apply my exponent rules to simplify this here. Okay, so this question here is really testing out our algebra skills. So here, 5 to the 1 divided 5 to the 1/3. So 1 minus 1/3 is 2/3. So I've got 5 to the 2/3 times 2 to the 1/3. I see my same denominator there, so same type of root. So I'm going to write 5 to the 2/3 as 5 squared to the 1/3. In other words, the cube root of 5 squared, which is 25. And this, of course, is the cube root of 2. And we remember how we can multiply radicals. So the product of 2 radicals is just the radical of the product. So this is the cube root of 25 times 2, 50. And there's my answer. Okay, so nice review on working with radicals. So now in B, okay, they actually give us the graph, okay, but we notice we didn't actually need it to solve A. Okay, and the graph looks something like this. Okay. Now, one thing I'd like you to notice is that in the past, when we saw stuff like corners or cusps, we always saw them within the context of a piecewise function. But here we see we have a non-piecewise function, which can give us a cusp, in this case here. Okay, so what they want us to find is they want us to find the value of A, okay, where we have this horizontal tangent. In other words, we need to determine where the derivative is equal to 0. Now, not only have I found the derivative, but I've also simplified it here. So f prime at x we managed to write as 10/3 times x to the negative 1/3 times x minus 1. Okay, so again, I'd like you to just notice that here this would give you 1 over cube root of x, okay, which means this derivative is not defined at 0, as we should expect with a cusp there. Okay, so when is this equal to 0? This cannot be equal to 0 since the x is in the denominator, so x equals 1 is the only value where you're going to have a horizontal